Thanks to the organizers for the invitation. So I'm going to talk about some connections between graph products, Artin groups, and lots of nice geometry that's around them. I was actually a bit worried this morning when I saw Mike's talk. Thought I might have to completely rewrite mine because of some overlap. There's going to be some things in common, but there's going to be a slightly different. Thank you.
At East.
So I'm gonna start by talking a bit about the geometry of some of graph products of groups. And to keep up with the tradition that has been introduced this morning, I'm going to use completely different notation. So when we want to define a graph product of a group, let's start from a finite simplicial graph, and every vertex V has a group GV associated to it, and to this data we can associate the graph product that I'm going to denote G sub gamma to keep in line with the sort of notation for Cookster groups and Artin groups I'm going to mention in a bit, which is obtained from the free product of all the GVs by adding the relations that GV and GU commute when there's the edge between UV is contained in gamma. Okay, and we'd like to understand these graph products and from a geometric perspective. So do these groups act nicely on some spaces, ideally on some non-positively curved complexes, and try to leverage that geometry to say something about these groups. In the case of graph products of groups, there's already something that is quite nice. There's the first type of actions, which is actions on trees. So the first remark is that if gamma is not a complete graph, then graph product splits. And if gamma is complete, then we just have like a direct product of all the GVs that appear. So that case is well understood. So just like to give an example, if gamma is a pentagon, and I pick this vertex here, V, I can look at the star of V. So the neighbors of V, that's going to be my first subgraph gamma 1. I can look the star of V. I can look at the complement of V. Here's my second graph gamma 2. And what I have is a decomposition of G gamma as the amalgamated product of the graph product over gamma 1 star, the graph product over gamma 2 over the graph product over the intersection. And you could repeat, so now you've got smaller graph products over some graphs that are a bit easier to understand. You can, if they're not over a complete graph, you can decompose that further. So you've got these nice structures, and a lot of results about graph products of groups can already be obtained from sort of induction reasoning using this kind of Basser theory. We're going to be looking at another type of action, in a sense, a slightly more natural complex, because here you have to make choices. You have to pick a vertex and look at this particular decomposition. The second type of complex I'm going to be looking at is related more to the sort of the buildings that the Mike was talking during his talk. So for that, so I'm going to recall briefly so the polyhedral product structure that we can use to understand G gamma. So So what we're going to do is for every vertex V, we associate to it a pointed space. The name just YV. YV was with a base point star V, and to this we can associate the polyhedral product, which I'm going to denote S gamma, because I'm going to indeed look at the connection with the Salvetti complexes in a bit. So the way it was defined this morning, it was kind of a subset of the direct product of all the YVs, which is fine. It's going to be another way to look at it. The way I prefer to think about it, and the connection with general Artin groups is maybe going to be a bit more natural from this perspective, is to look at it as the union of, wait, maybe some notation before I do this. For every simplex delta inside the flag position of gamma, we're going to associate just y delta, which is just the product of all these, when V is a vertex of delta, including an empty simplex, in which case I have an empty product, so it's just going to be a point, like a base point. And now for all the simplices in the flat completion of gamma, I can take the union of all these kind of sub-direct products, take their union and kind of identify them in the obvious way using various inclusions that you see. So instead of trying to give a formal definition of what this is, maybe just an easy example to understand what I'm talking about. If inside gamma you see, or even if gamma is just something like this, just two edges sharing a point, more color. So let's say this one is blue, this one is red. By the way, are the colors okay? Okay. So what I'm seeing essentially, so this, so the simplices in gamma flag, so gamma is equal to gamma flag here, and the simplices are vertices, but also the edges. So that first edge is going to contribute, should maybe say, all the YV are going to be circles. GV are copies of Z, say. So the first edge is going to contribute a circle cross a circle, so a torus. The second edge is also going to contribute a torus, but this one has two. So I see two base circle, one in blue, one in red. But the second one, I see one red and one green. And this identification that I mentioned here is just telling me that I should, because the red vertex is in common, I should identify this torus here with this torus here. So it's the union of two tori glued along a common circle, right? And that's, for people who are kind of familiar with rags, this is the Salvetti complex of that particular rag here. So that's the polyhedral product. I'm going to look at a slightly different, very much related, but slightly different object, which is going to help us make the connection with the buildings that were mentioned this morning. I'm going to look at a sort of extended version, for lack of a better name. So the various pieces that appear in this polyhedral product are kind of indexed by the simplices inside gamma flag, or the cliques inside gamma. And so I'm going to construct a new complex, but which is going to be a complex of space over the poset of simplices. It's going to give a bit more room to breathe to the space, and this is going to make some of the buildings appear more naturally. So let's introduce P of gamma is the poset of all simplices of gamma flag, including the empty simplex. And I'm just going to give a name to the geometric realization. So K gamma is going to be the geometric realization of early P gamma. So for instance, like if gamma is just an example that Mike gave this morning, 2 points and nothing else. So the simplices are, well, these 2 vertices and the empty simplex. So let's give them name VW. P gamma has V empty simplex W, and also see the inclusions with this, and so K gamma is just a subdivided edge. So what I want to see, and I was to think of my polyhedral product as something that lives above this complex here that parametrizes the simplices in gamma. So what I'm going to do is to slightly modify the definition that I gave here. So a simplex, so if I take delta, a simplex in A gamma, so a simplex in that geometric realization of that poset, that corresponds to essentially a sequence of inclusions of simplices of gamma flag. That part of, for instance, that edge here just corresponds to the inclusion empty simplex inside V. And so what I'm going to do, my new let's see, y delta extended, instead of so it's going to be defined as the smallest one, so y sigma 1 cross delta. So that new object lives kind of above delta. And now I'm going to do the same thing. I'm going to define the extended Salvetti complex as the union of all these. I'm going to draw a picture in a sec to make it hopefully much easier to understand. So I take their union, and again, there are a bunch of inclusions that are quite natural, and I'm going to use that to glue them together. So let's draw a picture so that hopefully it makes more sense. I'm going to draw that case, which is kind of the only one I can actually draw. I'm going to give some idea of what happens if it's slightly more complicated, but I can draw the whole picture for this one. So let's say gamma is this one. I'm probably going to need the whole thing. So let's go back. So let's compare a bit what we have here. So the Salvetti complex in that particular is here. So maybe let's mention that the groups I'm going to be looking at, the local groups are copies of Z. The YVs are going to be just a bunch of circle. So just a circle with a base point for each. So the Salvetti complex I'm seeing here is I've got my first circle for my first generator, but my second circle for my second generator. There's no further relation, so I'm just going to use the common base point to glue these two circles together. So what I get is a wedge of two circles, and that's indeed a space whose fundamental group is the graph product of this, which you mentioned, G gamma here. G gamma here is just a copy of F2. Two generators, there's no edge, so there's no commuting relation at all in here. Okay, so I'm just gonna draw as well the universal covers because just because I like drawing a tetravalent tree like everyone doing geometric group theory. Okay, stop here. And so I have my projection. This is S gamma, so that's the Salvetti complex that I guess everyone is familiar with, or at least this particular picture for the free group. Now, what is the extended Salvetti complex in that case? So, as I mentioned here, so the extended Salvetti complex is going to be a complex of space that lives above this subdivided edge. So I'm still going to see the first circle for my first generator, my second circle for my second generator. Also need something for the one corresponding to the empty simplex, which is just a single point for that single empty simplex. Now each of these edges, its associated space is going to be that edge cross the space corresponding to the minimal one, which is in that case is Y empty sets. So just an edge cross a singleton. So just an edge. What I'm seeing here is an edge, and here again an edge for the other one. And now what I have to do is to do the identifications of the natural ones. So what I see when I do that is just this picture. So it's kind of so in particular, the Salvetti complex, or the extended Salvetti complex, a kind of deformation retract or whatever onto this one here, just by collapsing the space K gamma that kind of parametrizes the various simplices. Okay, and in terms of universal cover, I'm gonna draw it as well because the picture is even funnier to draw. So I'm still seeing like a lift of the orange one gives me a line here. Because I'm seeing those lines at each point, I'm gonna see a bunch of, so you have to think in 3D now. Vertices in the green vertices in the middle. And at the end of each of them, I see fiber corresponding to the blue circles, which I'm gonna draw kind of horizontally, etc. And you keep going. And then you've got the vertical ones like this. You have to look at it kind of in 3D. If you collapse the white edges, you recover exactly this original tetravalent tree. The same way that if you collapse the white edges here, you recover the Salvetti complex. Right. But now let's do something else. So that's S gamma extended. But now there's another thing that you can do if you start from this extended Salvetti complex. Instead of collapsing the white edges, we're going to keep the white edges, and instead we're going to collapse the fibers. And if we collapse the fibers, still going to have a homotopy equivalence because the fibers are contractible. So collapse red and blue fibers. What I'm seeing is now every fiber becomes just one vertex in red or blue, we have a bunch of, so infinitely many edges or subdivided edges coming out of it. Now at the end of them, I've got the collapsed blue fibers, so blue vertices, etc. And the picture repeats at infinity. So that complex that we see here with the action of G gamma is actually the Basser tree for the splitting of that we have in our group, which is just a red Z free product blue Z. And downstairs, the quotient of this action is the same as if I start from the extended Salvetti complex. I collapse the red and blue fibers here. So the red and blue circles, what I get is just this picture, which is the same as the quotient of the Basser tree by the action of the group. Okay, but now, so this is the sort of buildings that Mike was mentioning in the first talk this morning. I've drawn the picture for Z star Z, which is kind of a boring group that most people understand without doing all this. It works exactly the same way for any graph product of groups. So let me just mention what happens if we do that more generally. So this can be done for any graph product. So what we're going to see is, so at a so we're still going to see S gamma, so the kind of the analog of the Salvetti complex, so the polyhedral product in the usual sense with its universal cover. In the middle, we're still seeing that notion of extended Salvetti complex with its extended universal cover. And on the right, so what is the analog of the Basser tree and its quotient? At the bottom right, the quotient is exactly going to be K gamma, so that complex that parameterized the various cliques in my graph. And upstairs, what we're going to see is exactly E gamma, which is the Davis building. For the graph product G gamma. Okay, so we have these very nice and we've got homotopy equivalence is everywhere for the horizontal arrows, since every time we're collapsing, what am I saying? There, upstairs, we're collapsing contractible fibers, so everything works nicely. So right, so why do we care about this? Or what do I care about this?
We're talking about graph products of Z's, so right?
Yes.
Artin groups, right-angled Artin groups.
Yes, but you can, yeah, but you can make it. That's yeah, that was going to be my next point. For if you just look at the rags, already the Salvetti complex is a nice cat-zero cube complex in its own right. So you can just use that geometry to understand that rag. And most people study cat-zero cubical groups from the point of view of their Salvetti complexes without looking at the Davis building, but you still can. If you look at another graph product where the groups are not necessarily Z, but they can be a kind of, you know, I don't know, what is your favorite ugly group or favorite pathological group, but you can take a graph product of these, and you can do the polyhedral product by taking the local spaces being just spaces with that group as a fundamental group, or even a k-pi1 for these groups, glue them together using the polyhedral construction. You still, that's kind of an analog of the Salvetti complex, still have the same picture here. But on the right-hand side, you can still see K gamma and the Davis building for that product. And that's the key difference here. This bit on the right is always going to be nice. You're always going to have a nice cat zero building, right-angled building that encode the geometry. Whereas on the left-hand side, maybe what I should mention is here really what we see is a proper and co-compact action of G gamma. So the geometry of S gamma tilde really reflects the geometry of the group. That's always true. So in particular, if the local groups GV are kind of not so nice, the geometry of S gamma tilde is going to reflect that. By contrast, the action of G gamma on the Davis building is not going to be proper in general. It's just co-compact. It's always co-compact. But the stabilizers are essentially the product of the GV for the various subdirect products that appear naturally when you
This thing you're calling the Davis building is just, you take the polyhedral product of these cones and then the universal cover.
Yeah. So this is always going to be at 0 and always a building, whereas this not always. So in a sense, and kind of the stabilizers are reasonably well understood in terms of the stabilizer of the local groups you started from. So in a sense, heuristically, you can think of a graph product as being kind of non-positively curved. I was going to say relative to those groups, not a relative in the geometry group theory theoretical sense, more like non-positively curved away from the GVs and the various products that appear naturally. So in particular, you can really try to use the action of a graph product on this nice cat zero space, even when the GVs themselves are not so nice, to try to understand the structure, the subgroups, the automorphisms, etc. Okay, is that first part kind of okay for everyone, or? Yeah.
So if you take the YVs to be classifying spaces for the GVs, S gamma always a classifying space for the.
Yes. For graph products, yes. It's yes.
That's what I called theorem 2 here.
Yes. Well, I can't remember the number, but yes, it's one of the. Yes, that was mentioned in Mike's talk this morning. Other questions?
So when you say can be done for any graph product, you mean the polyhedral product? You mean the pair space? Another one is the base point for.
Sorry? So you can always do that construction where instead of the YV being copies of circles, when the group is Z, you can do it.
Circle S1 and the base point.
Sorry?
I mean the polyhedral product associated with the S1 and the base point.
Yes. So now if GV is, I don't know, Z mod 2, for instance, you could take a projective space with a base point that has Z mod 2 as a fundamental group, or you could take infinite projective space if you want the classifying space instead with a base point, and then do those constructions again.
So the second space always be the base point. Can it be any subspace or not?
In the case I'm looking here, the second space is always just a point.
Thanks.
Okay, so
I was doing it with a second space.
sorry.
I had a second space. That would, it can be a second space.
There can be.
So,
In this talk, there shan't be.
sorry,
Yeah, you can work with the second space, but I'm gonna take the lazy route there and just go space with a base point and do the construction like that. So just to give another, maybe what happens, I mentioned the case of a pentagon. If you are looking at a graph product of Z above a pentagon, just to give an idea of what this sort of space looks like, what you're going to see is bunch of tori being glued together. And to glue them together, there's going to be a bunch of cylinders. I'm just going to draw these first ones. So for instance, if here I've got a red one, a blue one, and something else that I've not drawn yet, then I'm going to have, say, oh, maybe I should have, so red, and yeah, I'm just going to draw this part. Red and blue, it's that one here, the torus here, red and green. It's that torus here, and here the cylinder here is going to be used to glue, identify the red circles here. So it's telling you how to glue a cylinder between the tori. So instead of identifying circles between two tori, now we're gluing a cylinder between them. And on top of that, I also have the simplices coming from the empty simplex, and that's going to give me essentially a polygon, so a pentagon that I'm going to be using to glue along this thing. So it's going to be a bunch of tori, a bunch of cylinders between them, and a disc glued along this whole thing. I need that extra disc. If you don't do that, you don't get the right fundamental group, because there's a kind of a circle that appears here, so that would gives you an extra generator if you don't kill it using that pentagon. Okay, so that's for graph products. Let's move on to more general Artin groups and see what this diagram becomes, and what survives and what does not survive in terms of the nice geometries. Maybe I should recall briefly the definition of an Artin group, the corresponding Coxeter group. I'm gonna start with gamma, a finite simplicial graph. And every edge between two vertices A and B comes with a label, the MAB, which is an integer at least 2. And from this data, I can define the Artin group A gamma, which is given by generators and relations. The generators are the vertices of gamma, and for now, and the relations are, whenever I see an edge between two generators, I'm going to put a sort of generalized braid relation, AB, etc., is equal to BA, etc., where here I'm seeing MAB letters, and here I'm seeing MAB letters whenever the edge AB is contained in gamma. Okay, and there's another group that you can associate to this, which is the corresponding Coxeter group, W gamma, which is given by the same set of generators, the same as above, plus you require that all the generators have order 2.
Allowing maybe to be infinite.
Well, essentially, if MAB is no, I'm not allowed. So if I'm not putting an edge if the coefficient is infinite. All right, so maybe I should, if there are algebraists here, I apologize. There are two ways to talk about Coxeter groups and Artin groups. There's a Coxeter-Dynkin diagram, which is not this, and there's a presentation diagram, which is this one. So this graph is really encoding, if I see an edge, it really means that there's a relation that appears there. The Coxeter-Dynkin diagram is very useful to talk about classification of Coxeter groups and things like that, but it's slightly more awkward for us. So if you don't see an edge in the Coxeter-Dynkin diagram, it means that these generators commute. Right, so it's a kind of different way to think about these. So here I'm really looking at the presentation diagram that really encode the relations that I see in between my generators. Okay, and in this talk, I'm gonna focus solely on two-dimensional Artin groups. So an Artin group is two-dimensional if whenever I see a triangle A, B, C inside gamma, then the sum of the inverses of the labels is at most 1. So that's not the most natural looking definition, but it's actually a rather natural notion, and the two-dimensional is much more obvious when you rephrase it. It's the same as requiring that the virtual cohomological dimension of the corresponding Coxeter group is exactly equal to, well, is at most actually 2. It's equal to 2. So maybe I should say if it isn't free, so there's at least one edge, and whenever this. Right. So now you kind of see why there is it's called two-dimensional. The corresponding geometry is two-dimensional. Okay, and so now we want to do the same thing as what we did before, which is kind of associate an analog of the Salvetti complex, an analog of the extended Salvetti complex, and an analog of the Davis building. So the problem is, so it's slightly different now. Before, when in the graph product case, if I had an edge between two vertices, the corresponding group that I saw appear was the direct product of the two local groups. And the space that corresponded to this edge was the direct product of the two local spaces. Here, when I see an edge, for instance, an edge label 3 in the presentation graph of an Artin group, the subgroup generated by A and B is no longer a direct product. So for instance, for example, if gamma is just a single edge with an M at least 3 between two generators A and B, so it's no longer true. So A gamma is not equal to the direct product of the two copies of Z coming from the two generators. However, it's not too bad. The sort of groups that appear that way are not too bad. In particular, they are virtually Z cross FK, so finitely generated free. However, the Z that appears here does not come from one of the two generators. It's slightly more complicated element. So what we're going to do, so we're going to do the same thing as before. So we're going to kind of the generalization of the kind of both extended and non-extended polyhedral products. It's not really a product anymore. So now, so what are the let's say gamma. I'm just going to do it in the case of gamma is a pentagon to make it simpler, because I should probably, yes, still have time, but so what are the simplices that appear in gamma flag? So here I don't see any triangle in my graph gamma. So the only simplices that appear are, well, the empty simplex, one single vertex, or one single edge. Okay, so if I'm going to say that the the space corresponding to the empty simplex is just going to be a chosen base point. For one single vertex, YV, because my groups are still, the generators still generate a copy of Z in my Artin group, I'm still going to use a circle as a classifying space for Z. But now for an edge, if I see an edge between, let's say, A and B, so I need essentially a classifying space, ideally a classifying space, or at least a space whose fundamental group is exactly my Artin group on two generators and an edge M. And it turns out that for dihedral Artin groups, I can just take the presentation two complex corresponding to this, and that gives me a nice aspherical object. So I'm just gonna essentially take the presentation complex, two complex, which in that case is, let's say for simplicity, m is equal to 4, so I can actually draw something. So red and blue. I have one circle for my first generator, second circle for my second generator, and I'm gonna glue to this an octagon. Let's do it like that.
This one should really be called the Salvetti complex more than the one you.
Sorry?
This is the Salvetti.
Yes, yes, it is. Yes. In the case of Rags, it's also the Salvetti complex.
Yeah. You know, sort of. Degenerate case, this was the real Salvetti complex.
Yeah. It's a two-dimensional complex with just one two-cell that encodes that relation ABAB is equal to BABA, which is the defining relation for my Artin group. So this turns out to be an aspherical two complex for my group. So it's going to be kind of my local space. And out of this, I can define in a similar way S gamma, which is again the union of all these Y delta modulo inclusion. I can also define, well, S gamma extended. And so what is the picture that I see now? Yep.
That convention, if you have a triangle.
Yes.
What does that say about the geometry of what you just constructed?
If
Does that have any, the condition that the sum has to be less than or equal to 1, but does that have an implication on the geometry of the put together there? Because you're using the relation,
Yes.
Yeah.
So
posing something about the.
yes. I mean, well, what do you mean exactly by is that
I mean, does it say something about the homotop?
It says
so it's gonna
the angles in the triangles is less than pi or not, and so you can use like hyperbolic or Euclidean
Oh,
triangles when that's true.
but so
I see, okay,
in particular, this is gonna imply that your Artin group has cohomological dimension exactly 2.
okay.
Okay, so if you allow other types of triangles, for instance, if you allow 2, 2, 2, triangle with 2, 2, 2, then that gives you a Z cube inside your Artin group. So you know that it has cohomological dimension at least 3. So already that tells you that this has cohomological dimension 2. If the K-pi1 conjecture, no, actually that's always true. You don't need that. Being two-dimensional with that condition, this is equivalent to, for the Artin group to have also a cohomological dimension exactly 2.
Thank you.
You don't need the K-pi1 conjecture for this. Okay, so right, so I still have the same diagram. At least the leftmost part is the same. So the analog of the Salvetti complex and its universal cover. I still have the extended Salvetti complex and its universal cover. I can still do the same thing, the construction that I done before, where on the right I decide to collapse the fibers as opposed to collapsing the complex that encode the poset of simplices. I can still do that, and what I see on the right hand side is still the poset, the geometricalization of the poset of simplices. And what I see upstairs is, well, it just so happens I'm going to call it D gamma as well. But it's no longer the Davis building of the graph product, it's the Deligne complex, modified Deligne complex. Harry Davis complex, CD in that case, of gamma, right? So it's a very, and again, we still have all these equivalences above. So before I said that the Davis building is always a right angle at zero building, that was something really nice. It's no longer known, it's still conjectured. So the first remark, the fact that S gamma tilde, so the fact that S gamma is a spherical is equivalent to the K-pi1 conjecture. Essentially, the conjecture, the K-pi1 conjectures, this is a nice way of constructing. I mean, if you generalize that to all Artin groups, not just the two-dimensional ones here, if you, it's a nice way to construct an aspherical space for your Artin group. And by work of Trani Davis, it's equivalent to the Deligne complex being contractible. You kind of see already it appear here. You can kind of, because all these things are homotopy equivalent. And there's a natural question is that a nice way to prove that something is contractible is to prove that it has a cat zero metric. So is the Deligne complex cat zero? It's not known. Could be cat zero for the Mousson metric all the time, but at least it's yes in the case we're looking at here for two-dimensional Artin groups. And that's due to Trani and Davis. So in particular, something I was mentioning before, the geometry on the left is really the same as the geometry of the group, and we don't understand Artin groups that well. However, there are lots of cases where we know that the Deligne complex has a nice cat zero geometry, even though for instance, for general two-dimensional Artin groups, we don't have a nice geometric model for A gamma. However, we always know that the Deligne complex is cat zero. So you can use the action of the Deligne complex on this cat zero space, which is a nice co-compact, not proper action where we understand the stabilizers really well to say something about these groups. So I'm just going to mention that in the last few minutes, about how you can use that to, for instance, prove the Tietz alternative for these groups. There are also other things you could do. For instance, you can use that to understand the automorphism group of your group, or in the case of Artin groups, kind of solve the isomorphism problem, which is something that Vasco did recently. But here I'm going to just focus on the Tietz alternative. So the Tietz alternative is a very nice kind of phenomenon that tells you that in some cases the subgroups of your group are either really big, they contain F2, or really small, they're virtually solvable. So a group satisfies the Tietz alternative if every finitely generated subgroup either contains F2 or is virtually solvable. It was proved originally by Tietz for linear group, and it's been proved for lots of groups, especially groups that have some sort of non-positive curvature, non-positively curved geometry. In particular, there are lots of generalization or variation of the T alternative. You can strengthen this by requiring, for instance, instead of containing F2 being asynchronically hyperbolic or virtually surjecting onto F2. There are lots of strengthening. One that I quite like is kind of a non-positively curved version. The group satisfies the non-positively curved its alternative if blah, 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 instead of virtually soluble, virtually abelian. Which is more nicer, right? In particular, it's conjectured that non-positively curved groups satisfy the non-positively curved Tietz alternative. So there are a bunch of conjecture. So it's conjectured that if you take an Artin group, A gamma, at least conjecturally, it should be non-positively curved. It's unknown whether they're all cat zero. Some cases it's known that they are kind of systolic or heli, some notion of non-positive curvature. And if you believe kind of the Tietz alternative in general, it's also conjectured that non-positively curved groups should satisfy the non-positively curved Tietz alternative. So in particular, we could believe that Artin groups satisfy the Tietz alternative in one way or another. So there are cases that are known. It's open in general. So it's also conjectured. So it's known in some cases. So these Artin groups satisfy the Tietz alternative. So spherical type, or maybe the first one. So spherical type means that the corresponding Coxeter group is finite. And that's because they're linear. That's a result of Dean and Cohen and Wales that spherical type Artin groups are linear. So in particular, linear groups satisfy that is alternative, so do they. And well, the case we care about is the two-dimensional Artin group, A gamma. That's a result of mine from last year. I've done it with Piotr Czytycki in the slightly more general, slightly more restrictive case, like two-dimensional, and the Coxeter group is hyperbolic before. And there's another class that I'm not going to talk about today, but some people here may know it. It's called FC type Artin groups, which is due to myself and Piotr Czytycki, I don't know, 2 years ago. And so just to say a word about that case, the two-dimensional case, did that disappear? No, it's here. To prove the Tietz alternative, you really study the action of your Artin group on that Deligne complex, which is a nice cat zero a two-dimensional simplicial complex. In that case, I really try to understand the subgroups by understanding how they act on that complex. And you really need some specific tools because, for instance, you need to rule out the possibility that some Poisson subgroups for the Tietz alternative, for instance, infinite torsion groups that were mentioned this morning, these ones do not satisfy the Tietz alternative. So you need one way or another to show that these cannot happen or arise as subgroups of these groups. There are other types of Poisson subgroups that you need to rule out, but this is something you can do because there's really a lot of nice combinatorial structure that comes from the geometry of the Deligne complex. And the last thing that I'm going to mention, because it's a nice strengthening of the Tietz alternative for non-positively curved groups, was a notion introduced by Wise. So I'm going to say that a group satisfies the Wise alternative if for every group G, for every pair of elements A and B in G, there exists an integer n, at least one, such that A to the n or B to the n either commute or generate F2. So it's slightly might sound a bit weird at first. If you think about hyperbolic groups, the way we prove the T alternative for hyperbolic groups is generally you take two kind of independent elements. They might not commute and they might not generate F2, but if you take large enough powers, that's some sort of small consolidation geometry that occurs, and you can prove that these powers generate F2. If you take now a group that is non-positively curved but contains some flats in it, you can no longer expect that you're always going to generate F2, but the next thing that could happen is that these elements commute, that generate a Z or a copy of Z2. And it turns out that many groups actually satisfy this property, which might seem a bit strange at first. So for instance, so these groups satisfy Y's. So the first examples are rags. This is due to Bowdish in the 80s. In particular, if you have a virtually special group, it virtually embeds into a rag. So for instance, Coxeter group satisfy this. I guess I should put an eigenwise. Mapping class groups satisfy this. This is because of a result of Coperda that kind of relates the geometry of subgroups with the geometry of rags. And so some Artin groups do. So two-dimensional A gamma. I'm just going to put with hyperbolic Coxeter group. And this is due to myself. And again, you really prove this by understanding how these groups act on their Deligne complex. Do you see here lots of nice non-positively curved groups and groups I guess people care about? So a natural question, and it was actually a question asked by Wise in a list of open problems in geometry group theory. Do non-positively curved groups satisfy the Wise alternative? I mean, it didn't call it that, but you can call it that. So here, question: do non-positively curved groups satisfy the Wise alternative? You only phrased it for cat-zero groups and biautomatic groups, but you can really phrase it for any non-positively curved group. And well, no, it's not true for cat-zero groups, at least. There's a nice counterexample due to Leary and Minasayan from a few years ago, which is it's like an extension of Zn, so it's not something reasonably natural. So there exists cat-zero groups that do not satisfy this property. But a natural question is, if you have like groups that have a slightly more like a rigid or combinatorial structure, do these ones satisfy the Wise alternative? And it looks from what we see, at least in this list of examples, that many do. So it's maybe a question for you. Okay, so I'll stop here. Thank you.